If the p-value is above the significance level, then we fail to reject the null hypothesis. So, strange wording, but it means essentially that we accept the null hypothesis. However, because statistics is weird, it's not the phrasing that we use. We say that we fail to reject the null hypothesis. And the reason being is that it's the idea of we have not found enough evidence to prove that they are guilty. So therefore, we fail to say that they're not innocent, right? So that idea of innocent until proven guilty, when you if somebody goes to court and they're being charged with a crime, this idea of innocent until proven guilty, they don't ever say like, oh, well, then you're 100% innocent. They're just saying, we don't have enough evidence to prove that you're guilty. So we're just going to assume that you are not guilty because we haven't had evidence yet that's pushed us towards saying beyond a shadow of a doubt that you're guilty. So it's that idea represented in hypothesis testing, that if our p-value is greater than our significance level, we haven't found anything statistically significant enough in order to reject the null hypothesis, but it opens up to a potential for finding something else or calculating something else later. So we don't reject the null hypothesis and we don't accept the null hypothesis. We just fail to reject the null hypothesis. So the p-value is not the only value that you get back from your calculator. You also get back something called the test statistic, and this is either your chi-squared value or your t-value. And we always compare that one to what's called your critical value. And it's actually the opposite of what's up above. We don't do this with a t-value. We actually only do this with chi-squared. So if chi-squared is less than your critical value, so also less, instead of reject, we fail to reject the null hypothesis, versus if chi-squared is greater than the critical value, we reject the null hypothesis. You only have to do one or the other. You do not have to compare both the test statistic and the p-value to their comparable piece. If it says, hey, draw conclusions, you could either take the p-value or the test statistic and compare it. They will both give you the same answer. They won't have contradicting answers. They both come, the p-value comes from the test statistic. But there's further calculations that your calculator does in order to find that all at once. So they all come from the same number, so they will give you the same answer. You do not have to do both. Sometimes it'll tell you specifically, hey, compare the critical value to the test statistic, or they won't give you a significance level and they'll only give you a critical value. And then you're like, okay, I know I need to compare that to the chi-squared value. Or they won't give you a critical value and they'll only give you a significance level. And in that case, you need to have that p-value in order to compare. So do not ever cross. P-value should not be compared to critical value. Test statistic should not be compared to significance level. They should only be compared with this or with this. Another way to remember, if p is low, reject the h sub o. If p is high, we fail to deny. If p is high, we fail to deny. So just a little way to remember how this all works out. And then from there, it's kind of like opposites all the way around. And so that's how you can kind of remember how this all works when you get to your conclusions. A lot of talking. I'm sorry. We are almost done with me talking straight at you. The last thing we need to talk about is something called errors. We get errors sometimes when we run through on a test or when we process things mathematically. And there's two different types of errors that you can get. So we either know that our null hypothesis is true. Well, we don't know this for sure, but the two options are that either the null hypothesis is true or the alternative hypothesis is true. One or the other is true. And then we could either reject the null hypothesis or fail to reject the null hypothesis. So these are the truths, and then this is what we do, right? So either the null hypothesis is just, the null hypothesis is true, or the alternative hypothesis is true. If we reject the null hypothesis, that means that we accept the alternative hypothesis. So rejecting the null hypothesis when the alternative hypothesis is true is correct. That's good, right? We've done the right thing because this is true, and we've decided to say, yes, this is true. Same with failing to reject the null hypothesis. Failing to reject the null hypothesis means that we accept the null hypothesis, essentially, and that means that if it's true, then we've done a good job. Our test has been run correctly. However, we could potentially say, hey, we are accepting the null hypothesis to be true. So we would fail to reject the null hypothesis. If we accept the null hypothesis, but the alternative is actually true, that's an error. This one is called a type 2 error. I went backwards. This one is called a type 1 error. Type 1 error is if we said our alternative is true, but it's not. It's false. It's a false positive. So we said, hey, our alternative is true, but it's actually not. Whereas a type 2 error is a false negative, which we've heard of these before, right? Especially in terms of COVID tests, right? We can get a false positive saying, hey, you do have COVID, but it's actually not true, versus a false negative saying, hey, you don't have COVID, when in fact you do. So two different types of errors with two different types of repercussions. This, for errors, you do not need to know type 1 or type 2 errors. You will never see questions in this class about type 1 and type 2 errors. I've chosen to include this in this video because you will be talking about type 1 and type 2 errors if you take psychology, and potentially, I think also if you take biology or chemistry, you talk about these as well. The false positive actually has a pretty interesting connection with our significance level, which is that the significance level is the probability of a type 1 error. So to go back and for me to try a second time to explain to you the significance level, it's pretty much saying how much of a probability are we willing to accept in regards to error. So if we say, hey, a 1% significance level, that's a very small probability of error, right? So we're being much more strict about this test versus a 10%, which is still pretty strict. That's a small probability. That's a small number, right? 10% would be a little bit less strict of a test. And that means that we are accepting 10% possibility or probability that we will get a type 1 error. And so that's pretty much what your significance level is in terms of errors. Okay, so we're going to practice just a couple of things. We're going to kind of see what types of things that we would care about in regards to hypothesis tests. And then we're going to practice drawing conclusions. So the only thing we're going to practice today is how do we draw a conclusion. Okay, so all it says is state the conclusion of the hypothesis test. Guy wants to find out whether he spends more time on average playing computer games than his friends do. His hypotheses are his null, mu is equal to 1.2, the average is equal to 1.2. His alternative is that his average is greater than 1.2, where mu is the mean time in hours per day spent playing computer games. He uses a 5% significance level for the test. Guy collects some data and calculates the p-value to be 0.065. So we just want to have a conclusion for this test. So this is a t-test, just to tell you for when we're further down the line. This is 9.4 notes. It's testing averages. And so your t-test is testing like the average between two samples or the average within one sample. Did it change or did it not change? We have the p-value, and the p-value needs to be compared to what? The p-value should always be compared to the significance level, always. And notice they only gave us the significance level, and they did not give us the critical value, which was another hint. So the p-value is 0.065, and the significance level is 5%. 5% as a decimal is 0.05. So just remember that you have to turn your percent into a decimal. 0.065 is like 65, 3 decimal places. If I put in a 0 to also have 3 decimal places, if you have a hard time comparing decimals, this is a hack. That if you get the same amount of decimal places, then you can think of like, okay, 65 compared to 50, which one's bigger? 65 is bigger. But you can't do that unless you have the same number of decimal places. So if comparing decimals is tough for you, that you didn't realize that this one was actually larger than this one, then that would be something you can do. So our P is high, so we fail to deny.